Hi everyone, welcome to Kultrep. So here in this session, let us discuss about three-phase systems. So if you have any doubt like this, for example, so what is the balanced system and what is the unbalanced three-phase system? What is the floating neutral in the three-phase system? So how we can analyze the star-star connection, star-delta connection, delta-star connection, and delta-delta connection? So how we can find the power in a three-phase circuit? So is there any difference between the power in a single phase circuit or the three phase circuit? So let us discuss all these things in this three phase circuit analysis. So now let us start the session. So here, so let me take the three phase system. So from the very fundamental level, let us take the three phase generator in a black box. Let me take a three phase generator which can generate the three phase voltage. So now we are not going in detail into the three-phase generator, how it is generating the three-phase voltages and all. So we'll discuss it in missions. Now, so our main concentration is to analyze the three-phase circuits, right? So now let me take the three-phase generator. Three-phase generator. So let us assume that it is generating the three voltages VA, VB, and VC. So let it be the ABC, right? So now either this generator is connected in the star connection or either this generator is connected in the delta connection. So for example, if I want to represent in the star connection, it would be like this, right? Let me assume that this will be the three sources. So A, B, C. Star connected source. For example, if I want to make this generator into delta connected generator, so I will represent as a delta connected source like this. Delta connected source like, right? So let me mark the sequences A, B, C. So as we know that the single phase system has the phase difference of 180 degrees and two phase system has the phase difference of 90 degrees to get the rotating magnetic field as a constant rotating magnetic field. If it is a three phase system or more than three phase system in case of polyphase systems, so we will take the 360 by L, right? So what does it mean? So if it is a single phase system, so the phase displacement will be in phases will be the 180 degrees. So if it is a two phase system, the phase displacement between the two phases is the 90 degrees. If it is a three phase or more, so it will be the 360 by n should be greater than 2, and it will be the 360 by 3, it is 120 degrees. 120 degrees. So for example, if VA, VB and VC are there, how these voltages can be represented in the sinusoidal form? So VA equal to Vm sin omega t, right? So VB equal to the phase displacement between the two phases is 120 degrees. So it will be lagging by VB lagging by VA by 120 degrees. So we represented the sine omega t minus 120. And VC is Vm sine omega t plus 120 or minus 240. So either of the things we can represent. So minus 240 or plus 120. So VA and VB and VC can be represented like this. So if I draw the waveform for that, so how the waveform would be? The waveform would be like this, right? If I draw the VA and VB and VC, so if I draw the VA, VB and VC, so here, so the VA is the Vm sin omega t, which is equal to VA, it starts from 0, and VB is the Vm sin omega t minus 120. So it starts from after VA at 120 degrees, right? So it is VB, and VC is the, so after 240 degrees it will start from here. So it is VC. So here, what is the phase sequence? So the phase sequence is nothing but, let us understand what is the phase sequence of the three-phase system. So how we can define the phase sequence of the three-phase system? So for example, if I start from here at 0, if I start from 0, the maximum value of VA occurs at 90 degrees 90 degrees, and the maximum value of VB is occurs at 210 degrees. So the maximum value of VC will occur at 330 degrees. So what does it mean? So the order at which the maximum instance of phase voltages occurs is called as phase sequence. The order at which the maximum value of the phases occurs is the phase sequence. The first will be A, and then B, and then C. So if I represent in a phasor form VA and VB and VC, VA, VB, and VC. So in a clockwise direction, it will be the VA, VB, and VC. And each phase will be displaced by the 120. Each phase will be displaced by the 120. So here it is the positive phase sequence. If it is in this direction, we call this as a positive sequence. So what is the negative sequence? So negative sequence is nothing but one of the phase should be reversed. So for example, so if I draw the phase sequence like this, so VA and VC and VB. So now what is the phase sequence here? So here the phase sequence is ABC. And what is the phase sequence here? The phase sequence will be ACB. Now how the voltages will vary? So let me represent with the other color. So white color. So VA will be same. And this phase would be changed to VC. And this will be VB. So the phase sequence will be ACB. So which is called as a negative phase sequence and which is the positive phase sequence. ABC is the positive phase sequence. So now let us see what is unbalanced load and what is the balanced load and everything let us see. So for example, let us see so how the three-phase system is classified. So three-phase system is classified. So in a three-phase system, so it is categorized into three systems. So here, like balanced system, balanced three-phase system, or so we can call this as symmetrical three-phase system. Symmetrical three-phase system. And the second one is unbalanced three-phase system. Unbalanced three-phase system. Unbalanced three-phase system or unsymmetrical three-phase system. Unsymmetrical three-phase system. Unsymmetrical three-phase system. And third one is distorted three-phase system. Distorted three-phase system. So based on the connection of the, based on the connections, so it is divided into star connected three-phase system and delta connected three-phase system. So based on that, based on remaining things, so it will be defined like this. Now let us see what is balanced three-phase system. What is balanced three-phase system? So if the three-phase system has the same voltages and the same phase displacement, same phase voltage magnitudes and the same phase displacement, so we can call this as a balanced three-phase system. So what does it mean? Let us see. So for example, so all the three phases have the same magnitude. So if you find the maximum value of all the three phases are same. And if you find the phase displacement is so 0 degrees and 120 degrees and this one. So if the phase displacement 120 degrees and 240, the phase displacement in between it is 120 degrees and the value of the voltage magnitudes also same. So it is called as balanced system. Balanced system. So balanced system is nothing but it can be applicable for either positive sequence or the negative sequence. So either positive sequence voltages or the negative sequence voltages So don't get confused here. So positive sequence means balanced voltage, negative sequence means unbalanced voltage. It is not like that. So either it is positive sequence or the negative sequence. If the voltage magnitudes and the phase displacements will not affect it, voltage magnitudes and phase displacement is not affected. So we can call this as a balanced circuit or the symmetrical three-phase system. So balanced system is nothing but, so either of the positive sequence or negative sequence, the voltage magnitude and phase displacement should be same. So unbalanced system. So what is unbalanced three-phase system? So the unbalanced three-phase system is nothing but, so the voltage magnitudes are not same. The voltage magnitudes are not same and the phase displacements are not is 120 degrees. So we can call this as a unbalanced system. So for example, if I draw the three-phase system, so in case of unbalanced system, so for example, if I draw the VR, it will be like this. So after 120 degrees, VB will be start. So after 240 degrees, so VC will be start. So if these magnitudes are not same, for example, so VC will be like this, and VC will be like this, and VB will be like this. So for example, if the voltage magnitudes are not same, in the system, so here it will be here, and VB will be here, and VC will be here. So here voltage magnitudes are not same. Either it is a positive sequence or the negative sequence. So if the voltage magnitudes are not same, so we can call this as an unbalanced system, unbalanced three-phase system. So in case of unbalanced three-phase system or unsymmetrical three-phase system, so generally to analyze these systems, so what they will do, and this is the unsymmetrical system, they will change into symmetrical system like positive sequence voltage. So unbalanced three-phase system is divided into three symmetrical systems like positive sequence system and the negative sequence system and the zero sequence system. Right? So as we already seen positive sequence and the negative sequence systems, how they will be displaced. And then in case of negative zero sequence system, all the three voltages are the same phase. All the three voltages are same phase. VA, VB and VC. VA, VB and VC. So all the three phase systems are in the same. So distorted three phase system. What is distorted three phase system? So in case of distorted three phase system, what happens? So the voltages are not pure sinusoid. The voltages are not pure sinusoid. So here it contains some harmonics in the system, so which is called as a distorted three phase system. So this is how the three phase systems are classified. So now let us consider, in this case, let us consider balanced three phase systems. Balanced three phase systems. So here let us consider balanced three phase systems. So before that, to analyze the balanced three phase systems or unbalanced three phase systems, so in the future classes, so we will take an operator called A. So A is an operator we will use to analyze the unbalanced system. So in the fault analysis, for example, what is A? Let us see what is A. So we should understand this one, A. If you can find the A value and if you can understand the A, so you can easily analyze the three phase system, right? So now let us see. So what is A? So let me take A equal to 1 at an angle 120. What is the A value? A is equal to 1 at an angle 120 degrees, which is a simple operator, right? So it has a complex value of 1 and angle phase displacement will be the 120 degrees. So now what is A square will be? So A square equal to 1 at an angle 240. Right? So 1 at an angle 120 into 1 at an angle 120. So R at an angle theta 1. So from the very basics, R into R at an angle theta 2 if you take, so R square into theta 1 plus theta. So in the similar manner, it will be the 120 plus 120, it is a 240 degrees. So the same you can represent as a 1 minus 1 at an angle minus 120. 1 at an angle minus 120. So when A equal to, so let us find here, let us represent here. For example, so let me take other color. So let me take the white color. So here, I will take the reference positive and the negative. And let us take this as a reference. This will be 1. Let us assume this will be 1. So let us take this as a reference and let me call this as a 1. And here 1 at an angle 120 degrees minus 120 degrees is the A square. So minus 120 degrees is in this direction, that is the lagging direction. So it is the minus 120 degrees. So which is 1 at an angle minus 120 degrees. So what is this value? So which is equal to A square. So which is equal to A square. So what is the A square value? So here it is the positive and negative both are in the negative. So it is the minus 0.5 minus 0.86. Right? So for example, if I want to draw the A, how the A will be? So it is the 1 at an angle 120 degrees plus 120 degrees. So it will be in this direction. Or 1 at an angle minus 240 degrees. So 120 plus 120, it is in this direction it is negative. So in this direction you should consider it is positive. So which is equal to A. So which is equal to A. So what is the A value? So now y-axis is positive, x-axis is negative. So it is minus 0.5 plus j0.86. So root 3 by 2. Right? So what is that meaning? So cos 120 plus j sin 120. So minus 0.5 plus j 0.866. Now we got the basic formation. Now, so if I want to find the 1 plus a square. So what is the value? 1 plus a square. If I want to find the 1 plus a square, so what is the value? So for example, see here. So a is the minus 0.5 plus j 0.86. B is the minus 0.5 minus j 0.86. So 0.86 and 0.86 will cancel out if I add both. So minus 0.5 plus minus 0.5 is the minus 1. So 1 minus 1 will become 0. If I add these two, a plus a square plus 1, I will get the 0. So what does it mean? If the three phases are 120 degrees out of phase, so if we add the three phasors sum, so it should be equal to 0. It should be equal to 0, which is very important. So it should be equal to 0. So you can apply it in machines, you can apply it in the power systems also. So now let us see what is 1 minus a square. So for example, so here if I draw the minus a square, so where it will be? So a square is in this direction, so minus a square is in this direction. Minus a square in this direction. So where is the minus a? So minus a will be in this direction. Minus a is in this direction. So if I want to find the 1 minus a, so where it will be? So it will be here. 1 minus a. Right? So what is this phasor? 1 minus a. So how we can represent? So it is 30 degrees lagging. So it is 1 minus a is the root 3 at an angle minus 30 degrees. Root 3 at an angle 1 minus root 3 at an angle minus 30 degrees. So for example, if I want to find the 1 minus a square, so 1 minus a square would be here. So which is 1 minus a square. So what is the 1 minus a square? So 1 minus a square is the root 3 at an angle plus 30 degrees. So 1 minus a square is the root 3 at an angle plus 30 degrees. So for example, if I want to find the a minus a square, so a minus a square will be here. A minus a square will be here. Two phasors will be added there. So which is equal to root 3 at an angle of plus 90 degrees. If I take this as a reference, so it will be plus 90 degrees. So for example, if I want to find the a square minus a square minus a. So what is that value? So a square minus a equal to root 3 at an angle minus 90 degrees. Minus 90 degrees. So for example, if I want to find the 1 minus 1 plus a. Minus 1 plus a. So directly you can find, right? So what is this value? 90, and this will be the, so 90 and it will be the 30 and it will be 60. It will be 150 degrees. Root 3 at an angle 150 degrees. What is this value? It is minus 1, it is 1, it is minus 1, minus 1 plus. So that is a minus 1. Similarly, a square minus 1 also you can calculate. So now it is very simple. So if you understand the operator here. So this analysis is important to get easy calculations of the three-phase systems. So where A is an operator and A is the one at an angle 120 degrees. So we have find the A minus A square, 1 minus A square, right? So we have find the 1 minus A and we have find the A square minus A, and this upper circle will be the in terms of root 3. If you observe, the upper circle will be the in terms of root 3, right? So the lower circle will be the, so here it will be the 1 and here it will be the 1 at an angle 120. So here it will be the 1 at an angle, so 120, here it will be the 1 at an angle minus 120. Star connected system. So here, so we have the star connected three-phase system. So let me take the phase sequences A, B, C. Let me take the phase sequences A, B and C, right? So here let me mark this terminal as neutral terminal. Let me mark this terminal in neutral terminal. So here the source will be the VAN. Here the voltage will be VAN. So the line and neutral will be the VAN, and B and N. So let me mark this polarity is VBN. And if it is VCN, so here it will be VCN. This polarity will be like this. Now, so let us define what is the line voltage and what is the phase voltage. So here we have the three lines A, B and C. These are called as lines. For example, if the voltage in between, two lines, line to line voltage, if the voltage in between the line to line, so we can call this as a line voltage. So it is here, what are the voltages? A and B, that is VAB. VAB is one voltage, which is the line voltage, and VBC is the voltage. VBC is the voltage, and VCA is the other voltage. So VCA is the voltage. VCA is the other one. So we have the line voltages VAB, VBC and VCA. So now the line voltages are VAB, VBC and VCA. Right? So the line voltages are VAB, VBC and VCA. Now if I find the so phase voltages, what is phase voltages? The phase voltage is nothing but in between the line and neutral. So the phase voltages are nothing but, so the phase voltage is equal to the voltage between line and neutral, that is V line and neutral. So V line and neutral, we can call this, we represent this as a phase voltage, V phase. So what are the phase voltages here? So A phase and neutral is VAN. So VAN is the phase voltage. So from the B phase and neutral, if it is B phase and neutral, so it is VBN. If it is C phase and neutral, it is VCN. So here VAB, VBC and VCA are the line voltages. VAN, VBN and VCN are the phase voltages. Now, so here if you consider the star connected system, let us represent in the vector diagram, right? So let us represent in the vector diagram. So how can we represent in the vector diagram? Let me draw this in the vector diagram. And each phase here is displaced by the 120 degrees. So I will take VAN as a reference. So understand this point, which phase we are taking the reference is most important. Here we are taking the VAN, which is the phase voltage between A and N, we are taking as a reference. VAN we are taking as a reference, right? So VAN we are taking as reference. So generally the reference phase we will assume that the reference phase will start from 0 degrees. So if I write the VAN, if I represent with the V phase, so it is V phase at an angle 0 degrees. So we are taking the VAN as a reference. Now So the phase sequence, if I consider the phase sequence is ABC, so in the clockwise direction, ABC. So here the B phase will come, so which will be displaced by the 120 degrees. So it will be displaced by the 120 degrees. And so VBN and VCN are displaced by the again 120 degrees. So it is the VCN. So how we can represent these two? So VBN equal to, so because it is we are assuming that it is a balanced load. So VAN at an angle minus 120 degrees. Minus 120 degrees. So we can represent like this. V phase at an angle minus 120 degrees. Right? So how we can write the VCN? So VCN or VC equal to, so VCN or VC equal to VCN equal to VAN. So with respect to VAN, so how many degrees it is lagging? 240 degrees. So we can call this as a minus 240 degrees or so it is from this side it is minus 240 degrees. So if I go from this side, so that is, so here it is 120 degrees. So here it is 120 degrees. That means VCN leads VAN by 120 degrees or VCN lags VAN by the 240 degrees. Lagging by 240 degrees, leading by 120 degrees. So if it is leading, so we can write as a VAN at 120 degrees. Both are same. Both are same. So it is VAN, that is V phase at an angle 120 degrees. So like this, the three phases are represented. Now let us find VAB, line voltages. So here let us find VAB. Here no load has connected to the generator, just we are observing the voltages. So how the voltages will be? So here, now let us see how we can find the VAB. So here, if I want to find the VAB, so which is A is positive and B is negative. If I want to find the VAB, how I can find? So which is equal to, so if I apply the KVL in this loop, so what happens? So minus VAB plus VAN minus VBN equal to 0. So VAB equal to VAN minus VBN. VAB equal to VAN minus VBN. So VAB equal to VAN minus VBN. Similarly, if I want to find the VBC, so I need to apply the KVL in this loop, right? So which is equal to VBN equal to VBC equal to VBN minus VCN, right? So next VCA equal to VCN minus VBN. So now let us find one by one line voltage. Let us find the line voltages. Let us obtain the relation between the phase voltage and line voltage. So now let us find VAB from this. So first let us find without vector diagram. Without vector diagram also let us find. So VAB equal to so V phase VAN minus VBN. So I can write this as the VA. So I can write this as the VB. So I can write this as a VC. Right? So to understand, we put the VAN because the voltage difference between the VA and A point and N point. So here, let us find the VAB. How we can find the VAB? So which is equal to VA minus VB. So what is VA? VA is the V phase at an angle 0. V phase at an angle 0 minus V phase at an angle minus 120. So here, if I take the V phase outside, it will be the 1 at an angle 0 minus 1 at an angle minus 120. Right? This we have already found. What is this? 1 at an angle 0 minus 1 at an angle minus 120, which is nothing but 1 minus A square. 1 minus A square. In terms of A operator, we can find. So which is equal to V phase into 1 minus A square. So which is equal to 1 minus A square equal to root 3 at an angle root 3 at an angle 30 degrees. Root 3 at an angle 30 degrees. So from this VAB equal to, so VAB equal to root 3 times of phase voltage at an angle 30 degrees. VAB, right? It is VAB. So what does it mean? So the line voltage VAB equal to root 3 times of the phase voltage at an angle 30 degrees. So now, if I draw it in same in the vector diagram, how it will be? So let me draw in the vector diagram. So here, so now I just want to draw in the vector diagram. So here it is VBN is in this direction. So if I want minus VBN, it should be in this direction. So it will be the minus VB. Right? So how I can find the VAB? So if I apply the parallelogram, so here, so it will be the VL. And what is this angle? So it is 30 degrees. It is 30 degrees. It is 30 degrees. So here VAN minus VBN equal to VAB, and it is leading by in this direction. So in this direction it is leading. So leading by 30 degrees. Leading by 30 degrees. So what is the magnitude that we have find? So which is equal to root 3 times of the phase voltage. Root 3 times of the phase voltage. For example, if I draw the VBN, so VAB we have find, VBC if I want to find, how the VBC will be? So minus VCN will be here, minus VC1 will be here. So if I find the VBC, VB minus VC, VBC. So what is the angle between these two? It will be the 90 degrees, and VAB and VBC if you take, it will be the 120 degrees. So what does it mean? If I take VAB as a reference, so now I have changed the reference. Don't confuse here. VAB as a reference, what will be the VBC? So the VBC will be lagging by 120 degrees. VBC will be lagging by 120 degrees. So for example, if I draw the VCA, so VCA, so which is equal to VC minus VA, so it will be like this. So the VCA will be like this. So again, it will be 120 degrees out of phase with this VBC. So VAB, VBC and VCA, they are displaced by the 120 degrees. Now, let us write the expressions. Let us write all the expressions. Let us make the conclusion. So here, what is VA? We got the VA as V phase at an angle 0. Right? So phase voltage magnitude at an angle 0. So what is VB? So we got the V phase at an angle minus 120. So what is VC? So VC is V phase at an angle minus 240 degrees or V phase at an angle plus 120 degrees. Now, so we have find the phase voltages here. So now let us write the line voltages. So now what is the line voltage? VAB. So VAB equal to what we got? Root 3 into V phase. At an angle 30 degrees. So why it is 30 degrees? We have taken the reference vector as A phase. Remember that point. Reference vector is A phase. So VAB. So VBC. So what is the phase difference between the VAB and VBC? 120 degrees. So if it is minus 120 degrees, so what I have to do? Root 3 V phase. So already it has a 30 degrees. 30 minus 120, which is minus 90 degrees. So if I want to write the VCA, so which is equal to root 3 into V phase at an angle minus 90 already there. So it will be minus 120 degrees, or from here if you take, so it will be minus 240 degrees. What is the phase displacement here? Minus 240 degrees. If I substitute in this, minus 240 plus 30, so it will be the minus 210 degrees. So you can make it as a minus 210 degrees or so 120 plus 30. So it will be the 150 degrees. Root 3 into V phase into 150 degrees. Any of this you can make it. So this is how we'll find the line voltage and phase voltage. Line voltage and phase voltage. These are the phase voltages and these are the line voltages. Now what is the relation now? So if I make it in a single point, the line voltage is equal to root 3 times of the phase voltage. Root 3 times of the phase voltage. So the line voltage leads phase voltage by 30 degrees. By 30 degrees. So this we have considered as positive sequence. This we have considered for the positive sequence. If it is a negative sequence, what it would be the? So for example, if I consider the negative sequence, so what is the negative sequence? How the vector will be? So let me consider the negative sequence. So here, for a negative sequence, let us find. For a negative sequence, let us find. So we have find for the positive sequence, it will be the V line voltage. Line voltage leads the phase voltage by 30 degrees. So now let us find for the negative sequence. If I find for the negative sequence, so negative sequence is nothing but A, C, B. The first phase will be A, and the C phase and the B phase. VA, VC, and VB. Right? So here it will be the VA, VC, and VB. So here it will be the 120. So how we can represent the phase voltages here? So VA equal to, we have taken the reference as phase voltage. So VA equal to V phase at an angle 0. Right? So what is the VC? So VC equal to, now VC is minus 120 degrees with the A phase. Minus 120 degrees with the A phase. So it will be the V phase at an angle minus 120. So VB equal to, so what is the VB? So VB equal to V phase at an angle plus 120 degrees. Plus 120. Now the phase sequence has reversed. Now if I want to find the VAB here. So what is the VAB? So here it will be the VAB. So minus VB will come here. So if I find the VAB, it will be like this. VAB will be like this. So what is the magnitude will be VAB? Here VAB is, so before that in a positive sequence, the line voltage leads the phase voltage. In a negative sequence, the line voltage lags the phase voltage. Now, if I find the VAB here, how we can find the VAB? Let us. So VAB equal to, if I find the VAB, VA minus VB, that is V phase at an angle 0 minus V phase at an angle 1. V phase at an angle 1. So what does it mean? So which is equal to V phase at an angle 1 at an angle 0 minus 1 at an angle 120. Very simple if you know the table. For example, so if you concentrate here, you can directly write the expression without substituting anything here. So what is the 1 minus A? Root 3 at an angle minus 30 degrees. Root 3 at an angle minus 30 degrees. Now, if I write the expression, so which is equal to root 3 into V phase, at an angle minus 30 degrees. So which is equal to VA. So which is equal to 1 minus A. Right? So here VAB equal to root 3 into V phase into at an angle minus 30 degrees. So here let me draw the conclusion here. So either positive sequence or the negative sequence of the voltages if you consider, the magnitude of the voltage doesn't change. The magnitude of the line voltage doesn't change, which is equal to root 3 times of the phase voltage. But In case of positive sequence, the line voltage leads the phase voltage by 30 degrees. In case of negative sequence, the line voltage lags the line phase voltage by 30 degrees, right? So it is minus 30, there we got the plus 30. So similarly, remaining phases also we can find. So VAB will be minus 30 degrees. So if you write the VBC, VCA, you can find from that, right? Now, let us see the next one. So let us see the delta connected system. Delta connected system. Delta connected three-phase system. Delta connected three-phase system. So here we are just taking the generator only. We are taking the generator and load separately. So now we are analyzing the generator only. So we need to take the voltages only. So for example, let me take the sequence as ABC sequence. Here it will be the A, and here it will be the B, and here it will be the C, right? So here it will be the VAB, A is positive and B is negative, and VBC, P is positive and C is negative, VBC, and VCA, C is positive and A is negative, VCA. So this is how the delta connected system is represented. So here if you observe, the phase voltage VAB and line voltage also VAB. So in the delta connected system, the line voltages is equal to phase voltage. Line voltages equal to phase voltage. So we are just analyzing the voltages. Currents we will analyze in the later on this session. So here, so we got the line voltage equal to phase voltage because the phase is VAB. VAB is the phase voltage. If you take the lines also, it will be the VAB. So VAB equal to VAB, both are same. So it is the phase voltage equal to line voltage. So at this stage, the voltages are the line voltage, the phase voltage are same in case of the delta connected system. Now, if you draw the conclusion, in case of star connected system, the phase voltages are line voltages are root 3 times of the phase voltages. In case of delta connected system, the line voltage is equal to phase voltage. VL equal to V phase. VL equal to V phase. So now let us take the loads. Three-phase loads. Let us take three-phase load. Three-phase load. So what is the three-phase load? In case of three-phase load, we have the delta connected load and star connected load. In a three-phase load also, we have the unbalanced load and the balanced load. So what is the difference between the unbalanced load and balanced load? Let us see what is the difference between the star connected and the delta connected load. So it is the delta connected connection. So if I assume that, so let me call this as a Z1. So Z2. So let me call this as a Z1, Z2 and Z3. Right? So for example, here it will be the Z1, Z2 and Z3. Assume that it will be Z1, Z2 and Z3. If in each phase, the impedance in each phase, if the impedance in each phase is different, the current flowing in each phase also differs. So these two loads are called as unbalanced loads. So where Z1, either of the two phases are Z1 is not equal to Z2, so Z2 is not equal to Z3, and Z3 is not equal to Z1. If any of these condition is satisfied, the voltages, the phases will get imbalanced currents. So if it is imbalanced currents, so what will be the things here? So here we can call these two loads are balanced loads, unbalanced loads. So here, if the impedance on each phase are different, right? So if you consider what is balanced load, so let us consider the balanced load. If the Z1 equals Z2 equals Z3, if Z1 equals Z2 equals Z3, in these two cases, delta connected load and star connected load, if the three impedances in each phase are equal, that is Z1, Z2 and Z3, so we can call this as a balanced loads. balanced loads. So because if the balanced loads, if the three phases having the equal impedances and they are given by the balanced source voltage, balanced supply, so the current will be same in each phase. The current will be same in the each phase. So it is called as a balanced loads when Z1, Z2, Z3 are equal. So if Z1 is not equal to Z2 or Z2 is not equal to Z3 or Z3 is not equal to Z1, so we can call, if any of these condition is satisfied, so we can call that as a unbalanced loads. We can call that as a unbalanced loads. Now, so let us, in case of balanced loads, let us find the relation between the Z star and Z delta. Z star and Z delta. Let us take this one, Z star and Z delta. Let us take two cases. So let us find. So in case of case one, we have the delta connected load. So the thick lines are delta connected load. So let me represent with the Z delta. We have the delta connected. Now, if I want to find the equivalent star connected, so I can find. So because in DC circuits, in electrical circuits, we have derived. So right. So from that I can find. For example, it is a Z star, and this is also Z star. This is also ZY. So ZY, and ZY. So this is equivalent impedances of the star connection, right? So now if I want to find that this ZY, how I can find? Very simple, right? These two, Z delta and Z delta, Z delta into Z delta divided by the total impedances. Total impedances. So that is Z delta plus Z delta plus Z delta, which is equal to 3 into Z delta. So both will get cancelled out. So Z star equal to Z delta by 3. The equivalent star connection will be Z delta by 3. So if I can replace, if I want to replace this delta connected load into the star connection, equivalent star connection, I need to make this ZY is, Z delta by 3. Z delta by 3. So for example, let us consider the second case. So that's the first case. So let us consider the second case. Let us consider the second case. So here, if you consider the second case, so here, so let us assume that we have the star connected load. So we have the star connected load ZY, and Z. Now I want to convert into the equivalent delta connection load. So how I can convert into equivalent delta connected load? So it will be the Z delta equal to, for example, if I want to find this Z delta, so Z delta, if I want to find this equivalent Z delta, so I need to take, so Z star into Z star, that is ZY into ZY. So I need to add this ZY into ZY. I need to Z1, Z2, Z2, Z3 and Z3, Z1. So it will be the 3 times, and here it will be the opposite one. So opposite terminal will be the ZY. So here the ZY and ZY will get cancelled out. So 3 into Z. 3 into Z. So now if you find the relation, what is the relation? So the delta connected ZY equal to Z delta equal to 3 into Z into Y. So what does it mean? Very simple. If I know the star connected load, if I know the balanced star connected load, so which is having the equal impedance in each phase, which is equal to ZY. If I want to find the equivalent delta connection, if I want to find the balanced equivalent delta connection of the load, so I need to find Z delta. So with Z delta equal to 3 times of Z star. I need to replace with the 3 times of the Z star. 3 times of Z star. If I know the delta connection, I need to take the by 3. If I know the star connection, I need to take the into delta connection, I need to take the 3 times of the Z delta. So now, so we have seen the star connected load, star connected source, delta connected source, star connected load and delta connected load. So we have the possibility of connecting star, that is star connected source and star connected load, star delta, star connected source and delta connected load, delta delta, delta connected source and delta connected load, and delta star, delta connected source and star connected load. Let us analyze. So here star star connection. Let me take the star star connection. So what does it mean? So the star star connection means star connected three phase source, balanced three phase source is connected to the star connected load. So for example, so it is the star connected star star connection. So it is star star connection. So now let us see. So let us name the terminals here. So let me name this terminal as A, and this terminal as B, and this terminal as C. Right? So let me name these terminals as like this. So here it will be the VAN. If I may name this terminal as neutral terminal, so it is a VAN. So I can represent like this VAN. So if it is VBN, I can represent like this VBN. So if it is VCN, so I can represent like this. It is VCN. Right? So now in the load Z star, I will represent with a ZY. So ZY, assume that it is a balanced load. So ZY. So there are three terminals are there, three impedances are there. So we represent with the same impedance, which is equal to Z star. So now if I find the line current IA, so it is the line current IA, so which is equal to phase current, which is equal to phase current. So if I make this connect the common terminals, which is neutral terminal, so it would be like this. Now let us analyze this circuit. Let us analyze this circuit. How we can find the currents if the problem is like this. If the problem statement is like this. For example, so if you observe here, the VAN is the phase voltage and VAB is the line voltage. So in this case, so I want to find the phase current through the A. So here the phase current IA equal to the line current IA equal to, here it is the phase current. Here it is the phase current. So both the currents are same. Both the currents are same. So which is equal to line current equal to, in this case, line currents equal to phase currents. Phase currents. So in this case, line currents equal to phase current. Now I need to find the IA. How I can find the IA? So I need to find the IA. So which is equal to, so what is IA here? So the VAN is applying across the Z. So here IA equal to VAN divided by Z. So IB equal to, so IB is the current flowing in this circuit. IB, if I find the IB, so the voltage across is VBN. So here IB equal to VBN divided by Z. VBN divided by Z. So IC equal to VCN divided by Z. VCN divided by Z. So now this phase current is equal to line current. So line currents also will get the same values. So here, so what is the VAN? If I assume that it is connected as inductive load. So for example, Z star is, so the magnitude ZY at an angle theta. So assume that the value of impedance is inductive in nature. So now, so if I find that, so VAN, we know that VAN is, if you take the VAN as a reference, it starts from 0 divided by ZY at an angle theta. How I can find? So simple, V phase by ZY at an angle minus theta. Simple, V phase by ZY at an angle minus theta. So if I find the VBN, so which is equal to V phase at an angle minus 120 divided by Z at an angle theta. How I can write? So which is equal to V phase by ZY at an angle of minus 120 minus theta. Minus 120 minus theta. In the similar manner, so it is 120, 240 degrees out of phase. So it will be the V phase by Zy, magnitude of Zy, so at an angle of plus 120 minus theta. So this is how we'll find the IA, IB and IC in the circuit. Very easy. It is easiest circuit. So for example, if I want to find the neutral current, so how can I find the neutral current? For example, if I assume that neutral current is in this direction. So IC is in this direction. So IA, IB and IC and the neutral current, all the four currents are approaching to the common point. Right? So they are incoming currents. So I can write it as IAN equal to minus of IA plus IB plus IC. IA plus IB plus IC. So from this you can observe that IA, IB, IC are the 120 degrees out of phase. So for example, if I write minus, if I take IA as a reference, so IA at an angle 0. So IB I can write it as a IB at an angle minus 120. So IB, it is IA at an angle of minus 120. So IC I can written as IA at an angle of minus 240 or plus 1. So which is equal to, if I take IA as common, minus IA as common, so I can write this as a 1 plus A square. 1 plus A plus A square. What is the value of 1 plus A plus A square? So 1, A is nothing but 1 at an angle 120, A square is nothing but 1 at an angle minus 120. So if I add this, so it will be 0. So the neutral current is 0. Neutral current is 0. So as we discussed before, so if you want to find the VAB here, so VAB is the line voltage. The relation between the line voltage and phase voltage is, so phase voltage at an angle of 30 degrees. So root 3 times of the phase voltage at an angle of 30 degrees. So the line voltage is the root 3 times of the phase voltage at an angle of 30 degrees. So line currents are equal to phase currents. We can find like this. But now the condition is, so it is, let us assume that it is an unbalanced load. What is unbalanced load? If the impedances are in each phase is not equal, we can call this as an unbalanced load. So how the impedances are not equal? If impedances are not equal, so what happens? So let us assume that this is Z1, Z2 and Z3. So what happens? IA is not equal to IB, IB is not equal to IC, so IC is not equal to IA. So IC is not equal to IA. So in that case, the neutral current is not equal to 0. At this point, the neutral current is not equal to 0. Somewhere at point it will be 0, the neutral will be shifted. Neutral will be shifted if it is unbalanced load. So if I vary the Z1, Z2, Z2, Z3 and Z1 and Z2, Z3, so the neutral will be floats. So it is not constant and it depends on the load impedance values. So which is the condition called as floating of neutral. So which is an unbalanced condition. So how we can avoid the floating of neutral? So the floating of neutral can be avoided by, so if this neutral point, if I earth this neutral point, and the sub networks, how many networks that are connected to the source, there also we earthed and they are connected, they are interconnected. The sub networks also earthed. So what happens? It makes the earth potential as common, which is 0 potential, so which makes the neutral point at constant point. Neutral point is at the constant point. Generally, this problem occurs in the distributed networks, right? Now, so let us see the second case. So what is this? Star delta connection. So which is star delta connection. Star delta connection. Star delta connection. Now let me mark the terminals. So what is the star delta connection? Source is the star and delta is the load. So let me mark the terminals. A terminal, B terminal and the C terminal. So now, so here I will make it as a IAB. This current will be the IAB. This also let me mark as A, B and C. Right? So the current flowing through the A and B is IAB. The current flowing through the B and C is IBC. And the current flowing through the C and A is IC. Now let us find IA. So which is IA is the line current. IA, IB and IC. So IA, IB, IC are the line currents. So in this case, IA, IB, IC are the line currents. They are line currents. line currents, and IAB, IBC, and ICA are the phase currents. Phase currents, right? Simple. Now, so what is this voltage? VAN. If I make this as a N, so it is VAN, VAN, and this is the VBN, VBN, and this is the VCN, VCN. Now, so if you observe this circuit, the star connected source is connected to the delta. Now we need to find the line currents and phase currents. So if the problem came like, now find the line current and phase currents. So how we can find? So for example, if you take this AB phase in a delta connected. So what is the voltage applying across the star? VAB. So VAB is applying across from the star connection. VAB is applying from the star connection. Excuse me. So put VAB. Now it is VAB. So VAB equal to, what is VAB? So in case of star, it is a line voltage. So the phase voltage V phase at an angle 30 degrees. VAB equal to V phase at an angle 30 degrees. So what is the VBC? So if I find the VBC, the phase voltage into the phase voltage at an angle minus 90 degrees. So what is VCA? So VCA is equal to, the line voltage VCA is equal to the phase voltage so at an angle 150 degrees. 120 plus 30, 150 degrees. So these are VAB, VBC, and VCA. Now let us find how we can find the, let me call this as a Z delta, and Z delta. So now let us find the relation between the, IA and phase current and line current in case of the delta. Now let us find IA equal to, what is IA? So now assume this node, the current is approaching, IA is approaching, ICA is approaching, both are incoming currents, IAB is the outgoing current. So which is equal to IAB minus ICA. So which is equal to IB equal to, so what is IB? So IB equal to IBC, this is IBC and this is IAB. IBC minus IAB. So similarly, IC can be determined as, so IC, how we can determine IC? So IC equal to ICA minus IBC. So this is how we will determine the line current and phase current. So how we can find the IAB? For example, how we can find the IAB, IBC and ICA? Let us see. So if I want to find the IAB, so which is root 3 into V phase, right? Root 3 into V phase, correct it, root 3 into V phase. So for example, if I want to find the IAB, I can find it as root 3 into V phase, that is VAB divided by Z delta. So assume that Z delta is an inductive load, which is equal to magnitude of Z delta at an angle theta. Assume that. So now I need to find the IAB. So how I can find the IAB? So IAB equal to VAB divided by Z delta. VAB equal to root 3 V phase at an angle 30. Root 3 V phase at an angle 30 divided by Z delta at an angle theta. Similarly, I can find the IBC. So IBC equal to VBC by Z delta. ICA equal to VCA divided by Z delta. So now we can find the IAB, IBC and ICA. If I substitute here, I can get the line current. Now let us find the relation between the line current and phase current. So line current and phase current. So what is, let me take the IA as reference. So if I take the IA, which is equal to line current, so which is equal to IAB minus ICA. IAB minus ICA. So where IAB is the phase current. If I represent this one, so IAB equal to, if I take IAB as a reference, so I phase 0 minus I phase at an angle 120 degrees. 120 degrees. So which is equal to I phase into 1 minus A. 1 minus A. So what is 1 minus A? 1 at an angle 0 minus 1 at an angle 120. So we have already derived, which is equal to root 3 into I phase, root 3 into I phase at an angle of minus 30. Minus 30 degrees. So from this, what we can conclude? So from this, what we can conclude? So the line current is, line current in case of delta connection, line current is root 3 times of the phase current, root 3 times of the phase current, root 3 times of phase current. And line current lags the phase current. Line current lags the phase current. Lags the phase current by 30 degrees. By 30 degrees. So this is one method to solve. One method to solve. So why I have explained all these things. So for example, if the impedances are different also, so you can find that currents. You can find the currents. But the second method also there, so which you can apply easily. So the second method is also there, which you can apply easily. So let us see that one also. For example, which you can apply for your problem. Second method. So for example, if I convert this delta into star, so for example, see here, already we have derived. If I convert this delta into star, what happens? Z star equal to Z delta divided by 3. Z star equal to Z delta divided by 3. So for example, if I substitute that, Z star equal to Z delta by 3, so it is similar to the star-star connection. So you can find here, so in this case you can find as, so VAN, so in this case you can find as VAN as voltage source. So the line current can be found, line current can be determined, so like this. So IA is the line current. So line current, so it is Z star equal to Z delta by 3, Z star equivalent star equal to Z delta by 3. So whatever be the Z delta, I need to take the Z delta by 3, and it is a VAN at an angle 0. VAN at an angle 0. Now I can find the IA from this, which is equal to line current. So the only line current we can find. So VAN at an angle 0, that is VAN, or the phase voltage at an angle 0 divided by Z delta by 3. So this is the line current. This is the easiest method you can find, the easiest method to find the line current if it is a balanced load. So this is important. To solve the problems, we will apply this one. So this is important. So now let us see the next one. Delta to delta connection. So delta connection. Now let me explain you delta connection. Right. So now let me mark the naming. Right, it is the A phase, and this is the B phase, and the C phase. Right. So it is VAB, and this source will be VAB, and this source will be the VBC, and this source will be the VCA. This source will be the VCE. Okay. Now we have the load which is also connected in the delta, and let us assume this as Z delta and Z delta and Z delta, right? So the current flowing through A and B phase is IAB, right? So the current flowing to the B and C phase is IBC. So the current flowing to the C and A phase will be the IC. So now let us find the line currents and phase currents for this circuit. So now let us find the line currents and phase currents for this circuit. So it is very easy circuit. So here, in case of delta connected source, so the line voltage is equal to phase voltage. The line voltage is equal to phase voltage, which is equal to phase voltage. So the line voltage is equal to phase voltage. So VAB is applying across the IAB. If I want to find the IAB, so IAB, how I can find the IAB? So IAB equal to VAB divided by Z delta, right? VAB divided by Z delta. So similarly, IBC equal to VBC divided by Z delta, right? And ICA equal to VCA divided by Z delta. Right? Now we got the IAB, IBC, and ICA. So from this you can find the line currents, as we know that it is a delta connected. So previously we have derived IA equal to IAB minus ICA. So from that, if you derive, so IA equal to √3 times of phase current, √3 times of the I phase current. Let me write it as I phase, √3 times of I phase current, and it is at an angle of minus 30 degrees. Right? So the line current lags the phase current by at an angle of 30 degrees. In the simplest manner, you can find. So here line voltage is the phase voltage here, very simple. So and you can find the line current from this. So if it is a delta connection. So this we have already derived in the previous one. So here we have derived IA equal to IAB minus ICA. So from that you can find as the √3 into I phase at an angle minus 30 degrees. Now, so let us see the next one. So which is the delta star connection. Now let us see this circuit. So how we can find for this circuit, let us see. So here, so the source is delta connected and the load is star connected. So let me represent the source. Let me name the source as A, B, and C. Right? So we have the three terminals A, B, C. It is VAB, and it is VBC. It is VBC, and it is VCA. I will represent as VCA. Now the current flowing through the line, I will take it as IA. Here the current flowing through the line in the load also it will be the same current. So let me call this as a Z star, ZY. I will write it as a ZY and ZY and ZY. Let us assume that it is a balanced load condition. So here it is the neutral terminal. Let us assume that it is a neutral terminal. So IB, it is IB and it is IC. Now what we need to find? So we need to find the line currents and phase currents. So let us find line current and phase current. So here if you observe, the line current is phase current. In case of star connected load, the line current from the so delta connected source is equal to phase connected load. So phase of the star connected load. So now let us find. So here I need to find the IA. So how I can find the IA? So it is IA, right? So it is IB. Now if I apply the KVL in this loop, if I apply the KVL, will represent with a different color. So if I apply the KVL in this loop, So what will be the voltage equations? So let me write the voltage equations. So KVL in this loop, VAB equal to IA into ZY, IA into ZY minus IB into ZY, minus IB into Z, IB into Z. So here VAB is the here line voltage equal to phase voltage in case of the delta connected. So we can write it as the phase voltage also. V phase. V phase equal to IA into ZY. ZY, if I take it as a common, I can write it as a IA at an angle 0. If I take IA as a reference, IA at an angle 0. So minus IB at an angle of so IB is IA at an angle of minus 120. Minus 120. So if I take IA as a common, from that, so if I simplify this one, which is equal to 1 minus A, so 1 minus A, what is 1 minus A? So 1 minus A equal to root 3 at an angle of minus 30 degrees. So if I make it as IA into root 3 at an angle minus 30 degrees into Z star, Z1. So here from that IA equal to V phase divided by root 3, V phase divided by root 3, so V phase divided by root 3, so into an angle of minus 30 degrees. So here ZY also be there, ZY also be there. So this is how we can find the IA value from this. So the simplest way is, so let us find the simplest way also. So for example, if this star is connected to the star is converted into the delta. If this star is converted into the delta, the second method is if this star is converted into delta. So IRY, that is phase current, IRY or IAB can be determined as VAB divided by. So what is the equivalent delta connected? So it is equal to, if it is Z star, it will be the 3 into Z. 3 into Z. If it is converted into delta, it will be the 3 into Z. So it is 3 into Z. So now I can make it as a simple circuit. VAB, I will take one phase, VAB or V phase. So it is connected to the 3Z, and it is IAB. If I take one phase out, it will be like this. So from this, so IAB equal to VAB, that is VL equal to V phase here. So if I make it as a V phase, so V phase divided by 3Z. V phase divided by 3 into Z. So if it is V phase divided by 3Z is the IAB, that is phase current, which is equal to phase current. If I want to find the line current, IA, so IA equal from this IA if I find, so what it will be the, so line current is, so phase current into root 3, which is equal to, so phase current, line current equal to phase current into root 3, I phase into root 3 divided by 3 into Z. So root 3 and root 3 will get cancelled out. So which is equal to I phase divided by root 3 into Z. So as we know that the line current, so we'll get the same expression. Of this. Both are same. But it is very easy when compared to this expression, right? So follow the second method when you solve the problems. So it is equal to V phase divided by root 3 into Z. So this is how we will calculate the delta star connection. So now let us find how the power will be, how the instantaneous power, so how the active power and reactive power of the three-phase circuit carries power. So for that I will consider the three-phase source and the three-phase load. So let us assume that we have the three-phase source and the three-phase load, and they are connected. The currents are IA, IB, and IC, and the phase voltages are VA, VB, and VC. So here VA is assumed as root 2 V sine at an angle of theta V. So the theta V is the angle of voltage, so with respect to reference. So now similarly, we are assuming that it is a lagging load. So I consider it as a, so theta I is the current angle which is minus theta I. So similarly, so we have write the VA, VB, and VC. So here VA, VB, VC we have wrote. And similarly IA, IB, and IC also we have wrote. So each phase is differ by the 120 degrees. Now let us find the power. So how we can find the power? So how we can find the power? For example, power equal to, so VIIA each phase, VB into IB, and VC into IC. So now let us find VA into IA. How we can find the VA into IA? So for example, so to take the VA into IA, so VA into IA, so how we can write the VA into IA? So VA into IA equal to P of T equal to, that is instantaneous power equal to root 2 into V into root 2 into I, that is 2 into VI, 2 into VI, sin theta, sin omega t plus theta V, sin omega t plus theta V into sin omega t minus theta I. Right? So similarly, let us find the VB into IB. If I find the VB into IB, which is equal to 2 into VI sin omega t minus 120 degrees plus theta V into sin omega t minus 120 degrees minus theta I. Right? So similarly, the third term, so it is VC into IC. If I want to write the VC into IC, so VC equal to, so root 2 into V into sin omega t plus 120 plus theta V, so which is equal to 2 into VI sin omega t plus theta V plus 120 plus theta V into sin omega t plus 120 minus theta I. Sin omega t plus 120 minus theta I. Right? So now, so what we need to find? We need to simplify it. We need to simplify it. So here, so it is in the form of 2 sin sin. 2 sin sin equal to 2 sin A sin B equal to cos A minus B minus cos A plus B. If I wrote that, which is equal to, so 2 VI into cos A minus B. If it is A and it is B, so A minus B is the, so omega t will cancel out theta V minus theta I. So I can write it as a VI into cos theta V minus theta I minus cos A minus B minus cos A minus. What is cos A minus B? So it is the cos A plus B, which is equal to cos omega t plus theta V plus omega t minus theta I. So which is equal to cos 2 omega t plus theta V minus theta. So which is equal to, which is simplified. The first term is simplified. Similarly, second term. So if I write this for the second term, so which is equal to VI into cos theta V minus theta I minus cos 2 omega t. So here it is the minus 120 and here also it will be the minus 120. So minus 240 minus theta V minus theta I. Theta V minus theta. Right? So similarly, if you observe here, the third one is VI cos theta, VI cos theta V minus cos theta I, cos theta V minus cos theta I, minus, so if I take the third term, so cos into 2 omega t, so 2 omega t minus or plus here, so 120 plus 120, 240 plus theta V minus theta. So if I find the total power, total instantaneous power, so what happens? So these three terms, if you observe here, these three terms are 120 degrees out of phase. So if I add these three terms, what happens? 1 plus a square which is equal to 0. So and these three terms will make it as a 0, and if you need to add these three terms, we will get the 3 into vi into cos theta v minus theta. So which is equal to instantaneous power. Instantaneous power. So now, so what is the expression we got? So instantaneous power P equal to P of t equal to, so 3 into V into I into cos theta V minus theta I. So let us assume this as a pi, half a triangle pi. So we can write it as a P of t equal to 3 into V into I into cos pi. So it is equal to, so P in P of t. So here what you need to observe here. So what you need to observe here. So it is a three-phase power. It is a three-phase power. So for example, if I write it for the single phase, so already we have derived. So for the same expression, if I write for the single phase, how it would be? So P of t equal to Vi cos pi into 1 minus cos 2 omega t minus Vi sin pi into sin 2 omega t. So this is the expression we got. Right? So in a single phase, the instantaneous power is depends on omega t. So it is oscillating. But in case of three phase, it is independent of time. The instantaneous power is independent of time. So this is important. The instantaneous power is independent of time. Independent of time. So for example, if you take the single phase power, so it is also oscillating with the 1 minus cos 2 omega t. So both the powers are oscillating. So but average power is here Va cos pi, right? So now if you observe here, so here there is no reactive power component also. In an instantaneous power expression, remember this point. So in an instantaneous power expression, there is no reactive power component. And it's independent of time. But what we will do, so to get the mathematical expression, so physically in the instantaneous power expression, we haven't got any instantaneous power. But so to find the reactive power, so we need to apply some other thing. So here, if we simplify, if you write this as active power, that is power equal to three-phase power equal to, so we can write it as a root 3 into VLIL cos pi. Either star connected or delta connected load, we can use this formula. So either star connected load or delta connected load, we can use this formula. But in case of star connected load, VL equal to root 3 into V phase. Right? So in case of delta connected load, IL should be replaced with the root 3 into I. So this is generalized formula for star and delta connected load. So we can use this formula as root 3 into VLIL cos pi, where VL and IL are the line voltage. If it is a star connected load, we need to take the voltage as line voltage as root 3 into V phase. If it is delta connected load, so the line current is the root 3 into I phase. Now let us find the complex power. So complex power. Right? So complex power. So how we can find the complex power? So in the similar manner of single phase V into I conjugate, right? So we will use here 3 into V into I conjugate of I. So V at an angle, let us assume that V at an angle theta V. I is assumed as I at an angle theta I. So now if I apply that 3 into V at an angle theta V into I at an angle of minus theta. So it is equal to 3 into VI 3 into Vi into cos, so at an angle of theta V minus theta I. From this active power equal to, so active power can be defined as, so here 3 into Vi cos theta V minus theta, right? So here reactive power can be defined as, 3 into Vi sin theta V minus theta. So from the complex power we have done. But actually in the physical experience, so here in the physical meaning, there is no reactive power. There is no reactive power in the three-phase systems. If you consider overall three-phase system, there is no reactive power component. So it is included in the 3 VI cos. But so unlike the single phase, the three-phase power is not oscillating. It is constant and it is independent. So in a simplest way, so let me conclude the power, three-phase power. So for example, we have the three-phase generator. Assume that we have the three-phase generator connected to the, so let us assume that we have the three-phase power. So we have the three-phase generator, and it is connected to the, so capacitive load. Assume that it is a capacitive load, and it is connected to the capacitive load. So let us assume that it is connected to the capacitive load. So now, so what happens? So it is a capacitive load. It doesn't require any active power. So the mechanical power should be equal to, the mechanical torque should be equal to 0. Mechanical torque is 0. There is no mechanical torque is required. So there is only the reactive power. Is required. So to supply the capacitive load. So here there is a component of Q. So we cannot make it as in a three-phase reactive power. When you are explaining the three-phase reactive power to somebody, so don't tell that it is an oscillating power. So it is not an oscillating power. In a three-phase condition, it is not an oscillating power. It is constant. And in a physical meaning, it is not at all defined. So here, for example, for the same case, if I connect the single-phase generator to the capacitive load, what happens? So the power is oscillating. The reactive power is oscillating. So the power flows from the source to load and the load to source. Here we can define. But in case of three-phase system, it is an interview question. So in case of three-phase system, the reactive power is not an oscillating power. So and it is a constant. Right? So here the mechanical torque also is also oscillating in case of the single phase, but in case of the three phase, the mechanical torque is constant. If you connect the capacitive load, there will be the zero mechanical torque. So we can conclude this session. So tomorrow, so we can solve the problems on the three-phase circuits. So thank you so much. Thanks for watching the session.